Hello everybody. We are going to talk about electric fields, just the basics. We're not going to get too deep into them or electric field lines. We're just going to talk about the very basics of electric fields. If we think about a positive charge, we have a positive charge sitting there, it's not doing anything to anybody, just hanging around. Then we put another positive charge there. Well, immediately it pops off. It goes away right away. It's called action at a distance. In other words, it's a distance away and it gets and it acts. It repels. Well, action at a distance has a lot of problems. I mean, a lot of scientists just really don't like it for good reason. I mean, one, it implies there's some sort of extrasensory communication faster than the speed of light. There's some interaction that we can't see that happens following rules that we don't think we can follow. So people don't like that. It also implies that some forces are better than others. In other words, you push with your hand, you have to push to make it happen. There's like some amount of contact or whatever. This is like beyond contact. It's as if it knows that you're going to do it before you do it. And that's a problem. But there was a solution to it that Michael Faraday thought of in the 1800s. He said, well, maybe there's something already there. Maybe that there's not some sort of interaction like that. It goes there, it asks the other charge if it should repel or not. That there's already something in that spot, and we just don't know what that thing is. When the positive charge is placed, there's something in the spot, all the spots around it. And if you put a positive charge there, it'll repel. And that was already going to happen, regardless of whether you put a positive charge there or not. That there was something already there, so there didn't have to be any like new interaction or communication. Okay. And it could occur instantly, because the spot wasn't empty. It didn't have matter in it necessarily, but it had some sort of ability to act. That's what Faraday posited. And that stuff that's placed around the charge, that appears in all those spots, is what is now called the electric field. They tried a bunch of different things, but electric field ended up being the most popular version. So, if we have that positive charge, the definition of electric field is pretty straightforward. It's a proportion of the force applied by, or the electrostatic force applied to the amount of electric charge placed on that point in space. So I put a positive charge in that spot that we had in the previous slide, and if I had more electric charge there, I would get more electric force. So the proportion of those things, the force to that amount of charge I put there, is the electric field. It's a vector. It has a direction. It doesn't just point in whatever direction. The direction shows the direction of force on a positive test charge. So if I put a positive charge at that point, that's what I would get. I would get a force to the right if I put it in the spot it was in the previous slide. So the electric field not only has a number, like how much force there would be on it if I put it there, but it also has a direction, in this case to the right. The equation for it is just like it sounds. It's a proportion. E equals F over Q. But the little q on the bottom is not the charge of the object making the electric field. It's the charge of the approaching object, like I called it earlier, the test charge. Test charge is just a small positive charge, usually used to indicate the direction of an electric field. It can't be too big, because if it's too big, then it will have its own electric field, and that will interfere, and that will interfere in measuring. So it's just big enough that you can watch it, just small enough that it won't significantly change the electric field of the object that's making it. And the units are just like you would think. Forces in newtons, charges in coulombs. The electric field units are newtons per coulomb. Now if we have a point particles make their own electric fields. If we look at let's pretend that we have two charges, Q1 and Q2. Q1 is going to be our giant charge, and Q2 is going to be our point charge. Well, we know that what the force is between them. We also know what the electric field would be at that point. It's going to be the force divided by that approaching charge. So we're going to take the whole Coulomb's law equation, K, Q1, Q2 over R squared, and divide by the amount of the test charge, which in this case is Q2. It leads to an equation that looks just like you would think. E equals K Q1 over R squared. And it implies that electric field from a point particle is a lot like the electric force between 2 point particles. If you have more electric charge at that in that point particle, you get a larger electric field at a given spot. If you are farther away from the point particle, you're going to have a smaller electric field. If you double the distance you are away, the electric field will go down by a factor of 4. Some friendly advice is, just like when we talked about Coulomb's law, I said I was not putting the sign of the objects in the equation. I would recommend you didn't put the sign in there also. I don't want to go as far as for like an absolute value sign on it or whatever, but I want you to just calculate the number. You're going to actually determine the direction by looking at the situation and seeing what happens. Also, if you have lots of point particles, you don't have to despair. You can just add or subtract them, depending on the direction of the electric field, not necessarily depending on the sign of the charge that makes it, the point particle that makes it. I'll give you an example to show you two things that are opposite charges, but you end up treating them in a different way than you think. Let's say we have a point between two oppositely charged particles. So we got a positive charge on the left, we got a negative charge on the right. That little point doesn't have to have charge in it. In fact, that's the reason for electric field. It doesn't necessarily have a charge on it. It could, but it doesn't. Okay. The little point is a distance A from the left-hand positive charge and a distance B from the right-hand negative charge. The problem is, what's the magnitude and direction of the electric field at the point in the middle? I didn't say the exact center, although they do look pretty close. It doesn't have to be the center. A distance A from the point particle and a distance, or positive particle, sorry, and a distance B from the negative particle, just like it shows in the picture. Well, we're going to calculate the electric field at that little tiny point for each of the two charges. So for the first one, it's going to be E for the positive equals K, Q, because that's the charge, notice I didn't include the sign, over A squared. A is the distance from the center point to that positive charge. We'll do the same thing for the negative charge. E equals KQ over B squared. Again, I know I'm beating a dead horse here, but I did not include the negative sign there either. Now I need to look at the directions. And to do that, I'm going to consider putting a positive charge, a small test charge, where that little blue dot is. If I put a positive charge at the blue dot, it would be repelled by the giant positive charge, and it would point to the right. So it would, if all I had was that big positive charge, and I put a positive test charge at the little spot between the two, I would get a force to the right. So the electric field is to the right also. Now if you look at, let's just consider the yellow, the negative particle. The negative particle will attract a positive particle. So if I put a positive particle in the center between them, it would pull it to the right, which makes sense. So you'll notice, what are we going to have to do with the two charges, or the two electric fields? We're going to have to add those two together. It's the only way. Okay? Since they're the same direction, we have to add them. Again, it's got a giant summation sign, but it's going to be the sum is going to equal KQ over A squared plus KQ over B squared. Hope that helps with the problems. If you have any questions, feel free to email me.